of h of little x times, unfortunately I'll just do that. That's all I'm saying, all right? So, yeah. Unfortunately, the fonts are, I wish I could do this in LaTeX on the board. But the expectation of a random variable with a probability mass function px, I just take the summation, you know, it's equal to the summation over x of h of little x times the probability that big X equals little x. That's always true. All right? And here I'm just summing over two possibilities, a equals 1 or a equals 0. Because S is just 1 minus a. So the PMF is just only 1. You know? All right. So study those, you know, study the solutions and come back to questions.
So I guess one problem is
yeah.
that I keep on treating H as though it was like a Lyapunov equation. Like
oh, and H is any function, you know.
So we say that it's some
yeah.
function, and then we're basically substituting the value at some point into that function.
Right there, yeah.
And I understand that. I guess what I don't understand is H in this circumstance we say is rho. And then rho is a function of x, so that means that we have alpha over mu to the negative x at t plus 1.
Yeah.
But what I don't understand is how can you take the expectation up into the exponent?
You can't. Yeah. Several of you made that mistake. Yeah, several of you just did that. No, you got to do this. This is the only definition there is for an expectation for a discrete random variable. You sum over all possible points you can hit times the value of the function at that point. That's the only definition there is of an expectation for a discrete random variable.
Yeah, I guess I
yeah.
really then
yeah.
I do not understand this at all.
So
yeah.
Does the phi, which is a control action, have no effect in here?
Yeah, it does. I mean, phi was just equal to 1 or 0. You know, so
it's 1 and 0.
So phi of, well, this is just a particular example. The MM1Q, okay. This is just, you know, 1 if x is greater or equal to 1, and 0 if x equals 0. That's all. Yeah.
So that's for any kind of MM1Q?
No, there's only one MM1Q. That was the definition. Okay. Yeah, there's only one MM1Q. I mean, discrete time MM1Q is how we defined it. Yeah.
Because that's one of my problems. Was like, I thought I was you wrote it as a U in class instead of a Q, but
yeah, I know. That was.
I thought I was like specific to that example, and then the control. Or the control action was just like more general. Like
well, will be. I'm gonna go. I mean, our speed scaling example is like that, where phi is not equal to this. So in the MM1Q, this turns out to be phi, and it could be justified based on an optimal control problem. In fact, we might as well do that as an example. You know, not today. You know, you could say, well, why always work? You know, well, under the right optimization objective, this would be the optimal policy. You know? Yeah. So, yeah. Oh, you first.
In birth death process, can you write S equal to 1 minus a?
No. The birth death process isn't. Yeah, it's a generalization. So
that is also an MM1Q.
No, it's not. A birth death process is not a. It's not a model of a Q. I mean, it could be considered a model of a Q, but it's more general. Yeah.
The only difference that I guess I saw from the definitions that you gave on how it was not as constrained is basically just that alpha and mu can be time varying.
Yeah, not state varying. Yeah, so two things. One is that alpha and mu could depend on x, and you could also stay still. The probability of going from, you know, could be positive. So they're worth 3. Yeah.
It's interesting because the Wikipedia article on the birth-death process, like strictly, they have like a Markov diagram for it. They don't have any.
Well, they don't have any self loops. Yeah, no, they can have a self loop. Yeah.
You have to edit that.
Yeah. Yeah. Okay.
I mean, it seems like this is very trivial, and I just completely don't understand it. And it makes me feel a little bit crazy.
Yeah.
But so on the next step that you would do to try and prove this specific to this example for the H equaling rho, and as you have it written right here.
Yeah.
You would say now expectation of rho, you know, which would then be alpha over mu to the minus, and then that whole quantity inside of that would be x minus phi s plus a, right?
No, but the thing is, I mean, it's nicest to get into a form that's simplest, and this is the simplest. Because h of x plus 1, you know, I just, replace minus x by minus x plus 1, and the same thing here. Forget about x equals 0 for a while, so the plus isn't there. So this is the simplest one.
Apply that formula.
Yeah, which is this formula.
There are only two possible x's.
You go up or down, huh?
Yeah, because A and S are related like this. So either A equals 1 or A equals 0. So I applied this formula, where x is
So the first formula is more specific to the M1Q finite.
Yeah.
Of that general.
Yeah, this is for the this is a special case of that.
Formula which is specific to that case.
Yeah.
Okay.
Yeah, and this is a conditional probability. I mean, this is a conditional, but it doesn't matter. It's a conditional probability mass function. Big deal. Yeah. Yeah. All right. You just have to play with it. It's like, it is like I said, it's like a language.
But if you try to go the conditional probability way, you get stuck.
You don't, though, really. I mean, no, you don't, because this is equal to this, and then it might make sense just to substitute s equals 1 minus a, just to get your head straight, and look at two cases, either phi of x, just take x equal to 1, forget 0 for a second. There's two cases, either x is not 0 or it's 0. And so when you have this, you just apply this formula. And this has two options, a is 1 or 0. Okay.
And then eventually you can pull out all of the constants, and eventually you have expectation of rho to something again. And you have to do it the
So
same
you can
thing.
take out the row of x. That's the first thing I was able to take out. And for finding dh, then there's 2 row negative x.
Yeah. Yeah. So anyway, the thing is that some of you, like I was saying about, I mean, I feel your pain for those of you who are still suffering with the notation, but all it takes is doing a few more practice problems, and it'll suddenly click. Just take some stupid, boring problems and practice a few times, and a light bulb will go off. It really will. Because I've seen, every time I teach this course, there's a few people who are feeling like you are at this stage, and the light bulb will go off. Don't give up hope.
What would
Yeah.
be the next thing here?
The first line.
Yeah, this is definitely the simplest.
Yeah, just substitute.
Because
x
well, this
plus 1 in the row.
you get this from this.
X equation. So you get alpha over mu to the negative parentheses x plus 1.
Yeah.
Times alpha. And then plus mu times alpha over mu to the negative parentheses x minus 1.
Don't need that. Yeah. So yeah, the substitution. Just do the, forget it, it's much simpler just to forget the plus at first, and yeah.
So now, whenever you substitute those things in, though, now you have it to where pH would be equal to something that has a random variable still in it.
No, there's nothing random. No, this is conditioned on x of t equals x, where x could be 0, 1. It's not random.
But you have it, but x plus 1, won't it have?
No.
X and the
X is, say, 12, and that's 13, that's 11.
Change all the little x's to b's or something.
Yeah. Yeah, they're just numbers, or n or something. Yeah, it's not a bad idea. It's just an integer, a non-negative integer. I just changed all the x's to n's. They're just numbers. I want to know this conditional expectation for every integer n equals 0, 1, 2, 3, 4, 5. Yeah. Okay, so anyway, so we're going to go through another example. We're going to go through that example, the speed scaling model. Which is exactly the same as the M1Q, it looks like almost, except for not quite. So what are the differences? There was an S here before for the MM1Q. We could have put one in there. Yeah, but let's make it simpler. It wouldn't change things much at all. You know, so we could have so instead of having deterministic processing, there could be some outages. Occasionally, you know, I'm working, but nothing gets done at this time slot. A of t is arrivals just like the Q, so they're bulk arrivals. It could be nothing could come at one stage or 100 at the next. But here we had a cost function. So that's what makes things different. But you know, I'd almost feel guilty talking about optimization when the test is about not optimization. But this problem is so good for practicing this stuff again. It's just, it's fantastic. And so there was this average cost optimality equation. I'll write it like this for the fun of it. All right. So here we had a so you know, we've been using this generator, if you like. And I didn't use this notation last time. I used the P sub u. It's the same thing. So du is the same thing. And I'll remind you what that means. Okay, I'm not, you know. So it's exactly the same. Is that this is for any function h. So, you know, you go back to your notes. 8 star is called the relative value function. 8 star we'll see is an optimal average cost. I'm going to develop the theory later. You know, I'm going to go and play with this first. But this is just equal to at the suggestion of somebody in the audience, I'm putting crazy numbers here just to make sure they're really distinguished. Okay, you know. So before I had a conditional expectation only given the previous state, and you know, and let's assume n is an integer. You know, the x takes values 0, 1, 2, 3, and z takes in integers as well. If x of t is n, and u of t is z, I've just got an x minus z, all right? And that's just some ID sequence. Okay, and so we do the same thing. We'd have to use the formula that was suggested to a moment ago. So A's got a probability mass function. I guess I got to write it down.
If you are substituting xt equal to n, then it will be pu h n.
Oh, yeah. Sorry. No. Absolutely. No, let's be. Thank you very much. So I'm. Oh, and Z. Fuck you guys. Sorry. I'll never do that again. Okay. But if I take P, I put a subscript. You know, it's going to mean plugging into control, you know, and there'll be some abuse of notation. It's a tiny bit with this, but we'll wait on that. And then I'm evaluated at a particular state n. In this model, it's an integer, just like the MM1Q. Yes, you're right. Oh, God. So let's not do that again. But anyway, but this is correct, right? Because this is what I mean by an expectation. N is an integer, 12, say. Remember we said it was 13. N is 13, Z is 4. You know, these are just numbers. But A is a random variable. And A has the same distribution of any of these ATs. Because you know, the distribution of A doesn't depend on time. So it's got some sort of probability mass function. If that's the distribution of A. What?
Is that just for the sake of...
I was just saying it's just an integer, it's not random. Oh, I want to scream it's not random. So the only thing random here is this A. Yeah. You know, and it's got a probability mass function. And it's always for ID. If we have a Markov model, it has to be IID. Okay. Yeah. And so it's going to have some, you know, marginal distribution, they say, P sub A, and that's it. All right? And so you see how awful this damned equation is. You know, why I hate integers. You know, I hate the fact that you lose all the structure when you go to discrete state spaces and discrete time as well. Both those things hurt us. Because this equation, I'm taking a minimum over integers, you know, and it's actually u is less than or equal to x. That's to make sure that this is never negative. You know, it's a constraint you have to put in. And if I have to find 8 star, forget it. You know? So I mentioned last time, yeah, is that this is true for any h. Got it? So this guy here is on the state space. So x of t is in the state space. Again, 0, 1, 2, ... Again, that's one of the things that really gets me stuck. You know, I can't use all my calculus tricks. I can't take the derivative with respect to u and set equal to 0, for example, because it's a discrete thing, you know.
This minimization, that's just for one specific time step, right?
There's no time here. No, it's no time. Just like Poisson's equation, there's no time. A couple of you had little xt's in your Poisson equation. There's no time in Poisson equation. We know Poisson's equations like this without the minimization. It's just a fixed point equation, you know. And it's just now it's not linear anymore. Before we had like a matrix inverse, we could sort of.
The interpretation would be at time t. You solve this optimization
problem? No, not at all. No. Oh yeah, you're right. You get a state feedback policy. We'll come back to that later. The minimizer defines the optimal state feedback policy. We'll get a function for the minimum, which is a state feedback policy. Yeah. Now, I don't like integers, so I'll pretend I can extend this and have something differentiable. And I mentioned last time that you can go through and then use Taylor series expansions. You can hope you can't see that. So the only reason I'm writing gradient, well, partly because we can generalize this to, you know, state spaces in RD. But if I write h prime, you won't see it. Okay. So this is one dimension. This is GDX. Okay. Now, if h were quadratic, this would be exact, but I'd be throwing away a constant term. You know, but you know, constant terms, big deal. You know, yeah.
Could you mind again my H maps from?
No. This is 8 star. 8 star is not. 8 star lives on this damned state space. You know, this fixed point equation I'd like to solve. 8 star lives on the. Is only defined to the integers. Okay, but remember, I want to get insight. I don't want to just get a bunch of numbers. I want to get some feeling about how to solve these guys. You know, how much does the variance of A impact my solution? You know, things like that. I'd like to, you know, I don't want to just spit out a bunch of numbers, you know. I'll have no idea about anything. So what I'm going to do is I'm going to, remember my inverse dynamic programming trick, I'm going to try to find a approximate solution, but H is smooth, you know. And this is the main idea, is that this thing you didn't like, but this thing you probably doesn't bother you nearly as much. I'll show you. I mean, so the expectation of H of x of t plus 1 given x of t equals little x and u of t equals little u. So if this is true, then I can take the conditional expectation of both sides. All right? And this I'd have to go through, and I'd have to use this monster here and all that. Right? But here, if I take the conditional expectation of that, given everything, that's just h of x. So I did this last time. All right, so all I did is I took expectations of both sides, conditional on x and u. That's just h of x, because that's given. That's just grad h of x, you know. And then that, of course, is just x as well. But just go back to this. The difference is just minus u plus that. So, you know, if I can show you that I can really approximate the solution to this equation by something where this is really true, then you see my policy doesn't depend on anything but the mean of A, which is pretty damned awesome. That I don't need to know much about the arrival process at all. I know I've assumed it's IID, that's really strong. But the fact that I don't need to know anything but the first moment is pretty damned awesome. Number one. So you know, so this approximation only requires the first moment. Now, maybe I'm wrong. I find out, no, I'm wrong. Well, I can take a second order Taylor series expansion, and I'd find I need to know something about the variance of A. You know, and that happens sometimes. So this is just a way to think about these problems. All right. All right. The other beautiful thing. So conclusion one. Perhaps only the mean of A is significant. And by perhaps, I just mean there's hope if you could really justify this approximation. Right? But the conclusion two, which is so cool, is what I'm saying is that du, which is pulling this to the left-hand side, is just this old friend. So again, I'm repeating everything from last lecture, but if you go in and interpret this, you know, take the hx to the left-hand side, that's what I call du. All right? du just meant exactly the same as with Poisson before. You know, it's instead of taking the conditional expectation of h of x of t plus 1, I take h of x t. No, let me just do this. It's another colored pen now. Chalk. Just bring the h to the left-hand side. That's what I'm calling du. You know, and that's, so I've got the stochastic monster on the left-hand side, and the fluid ODE thing on the right-hand side. Okay. So that was the motivation last time for looking at this HDB equation, a deterministic approximation to this stochastic equation.
But are we still constrained to integers?
Well, we can fix that later. Okay. You know what I mean? It's like we can go. Well, the thing is that, we're gonna go and minimize this, yeah, and we're gonna get a minimum of 3.2. Yeah, we'll call it 3. and the thing is that when it's interior minimizer, there's not much sensitivity. You know, this is going to be some smooth function that we have to minimize, and it'll be incredibly flat. So when we
how does that approximation work?
well, I'm gonna. All right, shall we do it? Do we have time? Yeah, we have time.
15 or 18.
All right.
I was wondering because you're just you're linearizing.
Well, the thing is that we have to have some hope that H star is pretty flat. I know it's only evolved in defined in integers, but that it doesn't, But the thing is that if you think about this long enough, you find that with this cost function, like if you're forcing u to just be less than or equal to 1, you just get the MM1Q. If instead of saying u is less than or equal to x, u is less than or equal to 1, you basically get u is 1. You get the MM1Q. With that additional constraint, we've solved Poisson's equation, and we know it's quadratic.
How do we know that?
Yeah, but we solved Poisson's equation for the MM1Q.
Oh, okay.
Yeah, basically this becomes 1. It's just a constant. If we put an extra constraint, instead of saying u is less than or equal to x, we put a ridiculous constraint in the problem, say u is less than or equal to 1. You get a quadratic. I need some assumptions. I would need the mean of A to be less than 1 to get stability. But I get a quadratic. So you can kind of guess that this thing grows slower than quadratic. And you can play around and get some bounds. I could put a constant here. U is less than or equal to 5 or 6 or 7. And so I could justify this. And I could get bounds. And I could get all sorts of bounds showing that H star grows slower than a quadratic. We could show that. I may what's that?
What's J?
So this is just called the HDB equation. Well, let's interpret it. So I'll remind you. Can I kill this? Kill. All right, well, to answer your question, I have to finally stop lying. Last lecture, I was being slightly dishonest. Put a little 0 there. Why is that? Oh, forgot the min. What did you want me to do again? UT from 0 to infinity? That's what you wanted? No, it's okay. So the HGB equation, so this is a value function for a deterministic model. Very simple linear model. Only the minus sign, sorry, minus plus. The trouble is if you take the original cost function, it's never 0. Because if you get this to 0, I say, oh good, I can make u 0. Well, the thing starts to go upwards, because if u is 0, x starts going up. So we have to redefine the cost function. Take u minus its steady state value. So I did mention this last lecture. That's it's done in control of the time. You look at the deviation from the steady state behavior. So x is already the deviation from steady state behavior. We're trying to drive the system to the origin. If you get to the origin for the ODE, so if x is 0 and stays there, that's the cheapest place you can be, then u will have to be frozen at alpha. So you're just looking at deviation. And guess what? Back of the envelope calculation, x to the 3/2. So how this came about is we just said, well, let's try a polynomial. And then we, just by working things out, well, here's what we did. We said try j star of x equals some constant, say beta times x to the d. We knew that d had to be bigger than 1. We also knew that d was probably less than or equal to 2. And you plug this into here, and you get x to the 3/2. and there's a constant in front. I don't know. Do you want it? I don't want to do the algebra, or should I? Shall we?
C sub 0, just
It's
Again.
not C. You modify that.
So C of x was x plus. Oh, I see. There's an r there. Sorry.
Yeah.
Sorry. I forgot the. Yeah. Sorry.
matches up a little more, but
Yeah.
still.
No. But again, this will be infinite if I don't modify it. I need a little modification because this won't go to 0. So the only way for this to go to 0 is if xt goes to 0. But if xt stays at 0, then its derivative is 0. So ut must stay at alpha, which is positive. Yeah.
Okay, so we were changing.
We changed the cost function just a tiny bit.
Okay, all right.
Yeah.
We modified it
Yeah.
because we needed to make the problem make sense.
Yeah. Now there's other ways. The thing is that this actually, even if I left the original guy in there, this actually solves a different optimization problem, but way more complex. Instead of going from 0 to infinity, it's 0 until the first time hit the origin, and the solution becomes much uglier. So by changing the cost function, you get this incredible lock that you can just plug this
I'll
in.
take note of that on the exam when you give me a cost function.
Yeah.
I'll just change it to 1.
But I mean, I'll love it if it's not far off. I will love it. Yeah.
This one's too far.
But remember, our objective is just to try to approximate things. And so and we might as well do it. I mean, if you minimize this, so 0 is equal to the minimum over u of C0 of x plus the gradient of j star, which is d beta. Thank you. And then f of xu we said was minus u plus alpha. And see, I love calculus, you know? I mean, I can differentiate now. I can't differentiate those damned integers. And so it's a quadratic, and I differentiate. So I get 0 equals d du, you know? And the derivative of this, I'll get a 2r. And and then here I'll get a minus d beta and so get u is alpha plus something. So u is equal to its steady state value. And then plus d beta over 2r. And after all, it's just alpha I guess that's it, huh? Yeah. I mean, it's worth noting that it's sort of a gradient descent algorithm is what you get. I mean, this, you know, I'm just reminding you that what you end up getting is the optimal, this is the optimal policy of state feedback, and it's just a constant times gradient descent, the nominal value plus a gradient. But then you have to substitute this back in.
Would that be gradient?
No, because a minus sign. You know, you get x dot equals minus grad j star, you know, times a constant. You know, it's worth saying. But then you go through and you have to plug this back in somewhere. Yeah, you take this u and you plug it back in here. All right? Yeah, so here I got the u star, whatever, as a function of x. You know, that's the optimizer. And you plug it back in and everything cancels out. And that algebra I don't want to do in public. So I've got a handout for you all, and you will see that it is, drum rolls, 4/3 square root of r. Okay, there's all lowercase x's, you know. Okay, so when you plug this back in here, you can solve it and you get that.
Could you please repeat the u star equal to like alpha plus grad j star?
Oh, no, I'm just saying if you go back in here and you just forget everything, go back to this, just differentiate this.
Okay.
Yeah. I mean, it's just another point, yeah. You know, it would have been much better to say this first, and then say this. But anyway, when you take this optimizer and you plug it into this equation and you solve,
Do you get a differential equation?
well, that maybe that. And here you take that u star and you plug in here and solve. You find what the grad of j star is, and then you find j star. No.
So this all required us to assume J star is this form. So how?
Oh yeah, uniqueness of the solution to HGB equations. Take Jacob Hammer's course. You know.
Okay.
Yeah.
So it's always of that form.
No. Oh no, it is unique. So subject to growth rate conditions, the solution to this is one solution to that HGB equation, and it's unique among all continuously differentiable functions whose growth rate.
What he's asking is, what is the intuition that you use to pick out that form?
Yeah, on the line below that.
Yeah,
Try
J star.
J star.
Well, we knew.
Intuition.
I mean, why did we assume this?
Yeah.
No, we were just mucking around.
And we
got lucky. Oh yeah, it was incredibly lucky. So when we solved the other problem with the C naught, we just solved it. It's a one-dimensional differential equation. We solved it.
So I have a question.
And it's the same thing. But if you don't have the C naught, you can still solve the equation. You get this plus a linear term. So it's still. Yep. Yeah.
So if we were to form, because J star is defined as an infinite horizon interval right there.
Yeah, forget that.
Huh?
Yeah, that's what's defined, yep.
If you plug in that optimal policy, control policy into that, you will get that then?
Yeah, if you take this and plug it in here, you'll get J star.
You get the gradient.
But if you apply this state feedback policy, this is a policy, you know, we have a, so this is a function from positive, non-negative real numbers to inputs. And if you view this as state feedback, so U of t is equal to alpha plus blah times xt to the, d turns out to be 3/2. So this is the square root of x. That feedback policy will achieve this minimum. That's true.
Should we use a Lagrangian for u less than x?
No, not here. We don't need it. Yeah, this is all continuous time.
Yeah. I mean, instead of AJP, we could have used Lagrangian.
Yeah. So this is the optimal policy for this objective function. And I mean, this is like one of the luckiest examples, because you see what happens is, because this is j is x to the 3/2, where is it? Because of this, it's so damn flat that you can get it with murder. So yes, my assumptions were right. If I do a first order Taylor series expansion, it's not x squared. A Taylor series expansion is really valid. X to the 3/2, it's absurd. So near the origin, there's some error. But for x bigger than 2, why x bigger than, I don't know. I mean, it depends on the size of R. But for very small values of x, it's perfect. Absolutely perfect.
If x is smaller than u, will be greater than x.
And that's what you do. So here's what you'll find out. What can I erase? So this gives you if you could solve this monster, then for each x, the minimizer would define phi star of x, right? And it's only defined for integers, but I don't know how to draw a graph with integers, so let me interpolate. It's a perfect straight line for a while, u equals x, and then suddenly it becomes concave, which is what I saw in that talk in Caltech, some time back. If you actually plot this policy, what do we? I think in the notes I call it U fluid or phi j. It's not. It's as you all predicted. It's not feasible. It's bigger than x, right? And after a while, you can't see the difference anymore. They're on top of each other so perfectly. So if you just take the minimum of that with x, it's like it's so close to optimal. You've solved the problem. It's wild. It's just incredibly lucky. It's only because of the fact that Taylor series approximation turned out to be valid. So anyway, I'm preparing notes to pass out to you all, but there it is. So What time is it? Yeah, there's no time for it. I was going to actually just, next lecture we'll talk about value iteration, and this would be a good initialization then for value iteration. But I have to explain what that means. So I'll wait till next lecture.
Questions are due on the exam.
Yeah, well, the thing is that it's still stochastic. I intended to have it done by now, but I will declare 4 problems, and I will declare the last problem will be like short, questions.
Can we randomly sample our own stopping time?
You randomly sample your own stopping time if you can prove it to, if you can, and definitely go through the homework carefully. I mean, I noticed there's a bunch of the word variance comes up a lot, and the word and linear Markov chains comes up a lot, and MM1Qs come up a lot. There's lots of examples there that are obvious hints to how, questions. Yeah. So there's office hours now as long as you need me. I will sleep here tonight if necessary. All right. Yeah, I would say let's keep the room, but it's so stuffy in here. It's just horrible. But it usually is. But usually they're storming in by now, and they didn't show up last time either. So maybe they got smart and found another room.